right, we're going to continue looking at improper integrals. What we're going to look at now is what happens if one of your limits, so here either like a or b, um, is discontinuous at that point. So maybe there's like an asymptote there or something. So what we're going to do then is if you have that, then you are going to say that we're going to do the limit as you approach from one of the sides towards that number. Or if it is a, then we're going to do the limit as you approach a from one of those sides. So let's try some of those out and see what we get. So first example here, what's the integral of this? Well, if you check the limits here, you can see 2 is not going to work out well for us because 2 minus 2 is 0. We can't have division by 0. So what we're going to do here is rewrite this one then as a limit as x approaches to, well, actually, let's get some other variable in here like t, like we were using before. And then we have 5 to t now because we're doing the limit as we approach 2 for this one. And the other thing really we should probably put in a one of the sides there. So if we're going from 2 to 5, we would be approaching 2 from the right side there because 5 to 2 are coming in from the right. So now we're going to integrate this and solve it kind of like we did the last ones. So we got to figure out what's the best way to solve this. This one to me looks like a substitution one. Let's say u equal to x minus 2, derivative then being just 1 dx here. So if we make our substitutions, this would become 1 over square root of u du now for here. And then this would probably be easier to think of as u to the negative 1/2 as far as finding the antiderivative. And so that antiderivative would be u to the positive 1/2 because we add 1, and then reciprocal would be 2. We want to evaluate that at 5 and t. We still got our limit notation here. So if we put 5 in here, sorry, we got to do one more thing before we do this. We substituted here, so unless we change our limits, we do need to substitute back in here. So we want to have our x plus 2 back in here before we do this. X minus 2 to the 1/2. And for simplification purposes, I'm going to go back to the square root notation here. And we're evaluating that from 5 to t. So if we were to put 5 in there, that is just going to be 5 minus 2 is going to be 3, so we get 2 square roots of 3 if we put 5 in there. Minus, if we put t in there, we're going to get 2 square roots of t minus 2. So when we take this limit, now this is just a constant, so that's going to be there. We got to figure out what's this one going to be as we approach 2. Well, as we approach 2, if we put 2 in there, we're getting 2 minus 2, which is 0, times 2 is 0. So it looks like our answer comes out to be 2 square roots of 3. This does have a exact answer, and like we did before, we'd say this one is convergent because the amount of area is a finite number here. So here's kind of a graphical picture of this one. Here's the graph of square root of x minus 2 from 2 to 5. And there is an asymptote here, but this graph, as we continue up here, is approaching that fast enough that there is a finite amount of area in this, and that area ends up being 2 square roots of 3. Let's try another one here. So this next one, evaluate here. See if you can pick out which limit you think is not the good one here. All right, hopefully you picked 0 because natural log 0, that you can't do natural log of 0 or negative numbers. So we want to rewrite this one as a limit. We'll use t again as our other variable. So we're replacing 0 with the t. We're approaching 0 now of natural log x dx. And since if we go from 1 to 0, we'd be approaching from the right here again. So now we want to find this antiderivative. This one is the antiderivative is not 1 over x here. That's the derivative. If we're going to do antiderivative, this one would require us to do some integration by parts. Natural log's our first choice for u. That means the only thing left for dv would be to set it equal to dx. So our derivative that we take on this side would be 1 over x dx. Our antiderivative over here would be x. So now let's apply integration by parts formula here, keeping our limit notation. So we got u times v, which would be x, natural log x, evaluated from 1 to t, minus the integral still from t to 1 of v du, which would be x times 1 over x dx. That integral should simplify there for us because if we got x times 1 over x, that's just going to be, that just simplifies to just 1 here. So our integral now is just 1 dx. So antiderivative, that's going to be x. All right, so now we have to evaluate both of these because we found both the antiderivatives here. All right, so on the first one here, that's going to be 1 times the natural log of 1. Well, natural log of 1 is 0, so that's going to end up being 0 minus, if we put t in there, that's t natural log t minus this other one. If we put 1 in, we get 1. If we put t in, we get t. So now we have to, on this one, we're going to have to distribute that negative sign. And then we're going to end up with, here, this will end up being -1 plus t. And that one's easy to figure out as we go to 0. That's just going to be 0. Here's the one, though, that we got to do a little bit more thinking on. How do we evaluate this one? Because if we put, as we approach 0 from the positive side, t is going to approach 0. Natural log t is going to approach -infinity. That's an indeterminate form. So that should clue you in on, remember, we've done a bunch of these indeterminate form ones. This is L'Hopital. So we need to change this to a form where we can apply L'Hopitals, which you want to always have fractional form to apply L'Hopitals. Natural log is not easy to move to the denominator, but that t we could. So let's think of this one as natural log t over, if we move the t to the bottom, that would be t to the -1 or 1 over t. So now if we apply L'Hopitals, the top here would be approaching, we'd have like opposite of -infinity, which would be +infinity. As we approach 0 from the positive side of 1 over t, that's approaching infinity. Infinity over infinity, that's an indeterminate form we can use L'Hopitals with. So let's apply L'Hopital's rule to figure out our limit here. So let's indicate we're using it. So now this would end up being taking derivative as 1 over t. Derivative of the bottom would be -t to the -2. I still got this 1 plus t here. Now we should be able to plug 0. Well, let's simplify one more time here first. Limit. If we move this, well, one thing, we got 2 negatives, so it'll make it positive. Let's move that up to the numerator. So now I got 1 over t times t squared. That should just all simplify to only just t. So you got t minus 1 plus t. If you put 0 in now, you're getting 0 minus 1 plus 0 equals negative 1. So the area in this one is also convergent. Exact area is going to be negative 1. To see a picture of this one, here's the graph of this one. So here's the graph of natural log of x. You can see again, like we talked about with some of those limits, that's approaching negative infinity as you approach 0 from the positive side. The exact area here would be 1, but because it's underneath, we know that the answer comes out to be negative 1. Okay, let's try a trig one. So they want us to find the limit here. Secant, we know is the same as 1 over cosine. So this could also be written as 4 over cosine squared of x. So if you look at the two limit options, 0 and pi over 2, which one's going to make that 0? Well, cosine of 0, that one's okay. Cosine of 0 is 1. But if you do cosine pi over 2, that one's not so good. It just checking with calculator here, you can see cosine pi over 2 is 0. We can't have 0 in the denominator. So when we make this one a limit here, we want to replace the top one here. So as t approaches pi over 2, we're replacing that pi over 2 with t, and we want to evaluate this one. If we're going from 0 to pi over 2, we'd be approaching it from the left. I'm going to pull that constant of 4 out. So now we got to figure out how are we going to find the antiderivative of this one. Hopefully this one you know. Think about which function has a derivative that ends up being secant squared. That would be tangent. So antiderivative of this one is tangent. So we get tangent x. We want to evaluate it at t and 0. So now we got our limit here would be 4 tangent t minus 4 tangent of 0. If you're going to evaluate tangent 0, remember tangent is equal to sine over cosine. So it'd be what is sine of 0 divided by cosine of 0? Well, sine of 0 is 0. Cosine 0 is 1. So this part just going to evaluate to 0. Now we got to figure out the other one. What's the what does tangent of pi over 2 equal as you approach from the left? Tangent graph, you can graph this one out, but if you remember from trig here, there is some asymptotes here at, there's negative pi over 2. There's also one here at pi over 2. And the graph of this one looks something like this. That's a graph of tangent. So what is this one? As we come from the left, what is this approaching here? Looks like it's approaching infinity here. So this would be evaluated to infinity. So in this one, we get an answer of infinity, which is telling us this one is divergent. So the graph is not approaching fast enough on this one to have a finite amount of area. There's infinite area on this one. All right, why don't you pause it and try this next one, see if you can solve this one on your own. All right, let's see how you did here. So on this one, the one that's going to be bad is 0 here, so you want to replace that limit with t and then have t going to 0. And it'd be from the positive side here if you're traveling from 4 to 0. I also rewrote this function as x to the negative 1/2 there, so antiderivative should have been this. Now if you plug in your limits, we're going to get 4 and t, and x to the half is same as square root there, so I wrote a square root. The first one you can evaluate, square root of 4 is 2 times another 2 would be 4. This next one, if we do the limit as t goes to 0, that should just be 0. And so the answer is an area of 4, which is convergent. So hopefully you did okay on that one.